strictly convex shape. Okay? Okay, for this guy, I just have only a straight line. Just a straight line. So it's not concave, not convex, or it is concave and convex at the same time. Concave, yes, you are right. Concave and convex at the same right shape, at the same time shape. Because the linearity, the first property that we spoke about, if we have a linear function, so this linear function, it has the two conditions in it. So it is a convex and a concave curve. Okay, for this guy, as you can see, there is no points that's equal to each other, so it is a strictly convex graph. For this one, it's strictly concave curve. Okay, so it's strictly concave and concave also, because we spoke about that, they will accept the two cases. In this slide, you have more than one curve, and he wants you to link the equations with the curves. The equations with the curves. Some of them will be obvious for you, like the case of this quadratic function, for example, for this guy, okay, and for this guy also, they will be represented about this convex case. Otherwise, that's the solution of this problem. Otherwise, you will need to do further investigation, which can be done from preparing the Hessian matrix of each one of these matrices. Based on the sign of the Hessian matrix, we can classify this curve and link them together, each curve to the graph related. Now, for the extremum point and extremum. What we mean about extremum point, the extremum point is the input points. The extremum is the image value. فاهمين يا شباب؟ تاني عيد تاني. الاكستريمم بوينتس دي يعني لو بتكلم مثلا y equal to f of x، يبقى الفاليوز بتاعت الاكسات دي اللي بقول عليها الاكستريمم بوينتس. طب الفاليو اوفرول خلاص انا عرفت ان البوينت دي بيحصل عندها ماكسيمم بوينت. لو انا انسرتد هتطلع الفاليو بتاعت الفانكشن دي اللي بطلق عليها الاكستريمم. يبقى الاكستريمم فور ذا ايمج، الاكستريمم بوينتس فور ذا انبوت فانكشن اور فور ذا انبوت فاليوز. تمام كده؟ برضه انا قبل ما اخش في الجزء ده كنت عايز تسمرايز دول لبعض بالعربي. الستبس دي واضحه قوي. انا بعمل 3 steps عشان اقدر to identify the type of our graph if it was just maximum or minimum. The first of them هات الفيرست derivative. get the first derivative. يا اما الاكس واي يبقى بارشل اف بارشل اكس بارشل اف بارشل واي. السكند ستيب make this equation equal to 0 وحل السيستم ده. حليهم مع بعض. get the critical points. الستيب اللي بعديها هات الهيسيان ماتريكس. يعني انا هجيب السكند ديريفيتيف. بعدين اجيب الديترمنت بتاع الهيسيان ماتريكس. بعدين خلي بالك لما باجي اعمل كلاسيفيكيشن بعتمد على حاجتين. الديترمنت بتاع الهيسيان ماتريكس اوكي بلس الساين بتاع اف اكس اكس. لو الاثنين بوزيتيف يبقى مينيمم. لو الديترمنت بوزيتيف والاف اكس اكس نيجاتيف يبقى انا عندي ماكس. طيب لو الساين سادل بوكس ام سوري ليدن زيرو بتاعت الديترمنت يبقى انا بتكلم على سادل بوينت. اوكي اوكي perfect. We really finished all of this. Now for the definition, as I told you, it was explained in this paragraph. An extreme point of a ring function f is an argument of f. Argument of f, it means the input of f, whose image is at least as low or at least as high, as low once you are studying the case of minimization, as high once you are in the case of maximization. Okay, add the images of the arguments. So the images of the arguments stand for the extremum, and the arguments by itself stand for the extreme points. Now extreme points of f, once you have f of x, okay. This I need to explain to you. That's the meaning of minimum point and the maximum point. Okay, if I have the value, a specific value of f at a, and all the points in the neighborhood of this value is greater than or equal to f of a. This is going to be the case of a minimization problem. This is f of a, the crown. Okay, the crown of this one. All the points, all the other points in the neighborhood, f of x, the value, the images are greater than this guy. So this is going to be a minimization problem. Look, the converse or the inverse of this relation will happen once you have a concave shape. This is going to be the crown, which is the highest point, f of a. And all the neighborhood images will be less than this value. This is what's stated here. If you have f of x greater than or equal to f of a, then f of a is a minimizer. If you have f of x greater than or equal to f of a, then you will have f of a as a maximizer. Do you read me? Maximizer related to concave. Minimizer related to convex. So, okay, here we go. That's a problem which is x cubed minus 6 squared plus 9x minus 2. Look carefully to this shape. That's the shape of the function. By the idea, graphing this guy is very, very simple. Very simple. All I have to do is to try to get the points for this function, which is going to cut the x-axis. Then I will connect them together. Here is the 3 points. And then the curve will be between either going up, then down, and then up. This is the only way. Or vice versa. How to check getting any value within this interval, substituting in the function. If it was positive, it's done. Draw. So it's not a big issue to draw something like this. Now, according to our analysis, we have at 1 and at 3 2 points, while you have a maximum and a minimum point. Yes? Okay. The inequality that we explained states that at the neighborhood of the point 1, this is point 1, which is extremum point. So this graph have 2 extremum points, which are at 1 and at 3. These are called extremum points. Why? The values represent 1 or against 1 is 2. That's the extremum. And here also, the value in front of 3, which is going to be -1 or -2, whatever, it's going to be what's called the extreme. Remark that the value at 1, all the points in the neighborhood is less than this guy. We can state it by an open hoop. We can say that the open hoop around 1 is less than the value of the image at 1. Okay? This is what's stated here. 1 extreme point of f. Yes. Because if you have an open ball around 1 with a radius of 1, what's going to be the result? Every value of x will be less than or equal to the value of 1. It makes sense. All the neighborhood, look to the value of f of x. All the neighborhood of the point at 1, this is the maximum. The rest is less than this guy. So it's correct. Same way like it is the opposite if you went to the value at 3. Okay? So we have one extreme point of 1. Just a second. Here we go. This is about 3. Look to the point in the points in the neighborhood of 3. You will find them greater than f of 3, which means it's a minimization point. Okay? Which is it's a minimization extremum. Okay. If I took any values around the point 2, if you are from the right, then the values of the function by itself is less than the value at 2. And if you are from the left side, the values will be greater than the value of f2. So actually in this case, 2 represent a saddle point. See, if I took a 0.5 for example, the value here, the value of the function, are you sure? The value of the function is greater than الvalue عند 2 اللي هي بصفر. ولو جبت الياباني عند 2.5 هتلاقي 2.5 الفاليو بتاعتها اقل من كام؟ من 2 من الصفر. ايوه صح. يبقى ده معناه على طول ان انا عندي في الوضع ده saddle point. There is no extremum point and it's a saddle point. Okay? It's one of the critical points Remember, we used to get the first derivative, putting the first derivative equal to 0, getting the critical points. These are the critical points. How many critical points? For here, 2 or 3. If one of them approved that it is greater than 0, so it's a minimizer, less than 0, minimizer. But if it's equal to 0, in this case, I'm talking about the two function in one variable. Okay, it's going to be a saddle bond, which is the point at which the curve will change. It's an inflection point. It's concavity. If you remark, here the curve is going from this side into this side. So the monotonicity of the curve will change with this at this point. You read me? Okay, very good. Classification, we went through this, but I will summarize it once more. Strict local minimizer, it will happen once the neighborhood is greater than the value of the point. It will appear like this. Look at point A. This is point A. All the points in the neighborhood are greater than f of a. So f of x is greater than f of a. This is gonna be, this is called a strict local minimizer. Why? Yes. اللي قبلها اللي هي دي صح كده؟ بس ده لو انا بتكلم على جلوبال مينيمايزر، بس انا باخد مثال على مين؟ على لوكال مينيمايزر. ما هي النقطة دي with respect to its neighborhood is a local one. والنقطة دي with respect to its neighbor is also a local one. But globally it will be the first point. You are right, okay? Once more, if we talk about a local minimizer, so this is a strict local minimizer, just only a point. طيب, what's going to happen, or what's the case of a local minimizer? A local minimizer, not strictly local, it may appear like this guy, like this point. Okay? It has points equal to it, and then it is the lowest from the other side, for example. Actually, here the local minimizers are this guy, that guy, that guy, that guy, any something between this interval can be looked at as a local minimizer. Okay? Perfect. Right. Now let's start strict local maximizer, our maximum. It's going to be the same. Here we go. That's for point A. For point A, it's a maximum point because f of A is greater than f of x in the neighborhood of this point. Are you with me? Okay. For the local maximizer, it's something like this. It's not strict, but it is inside a certain interval and you have other points. And it's also a maximizing for the points from this side. Okay? So it's either equal or greater than. So f of x equal or greater than the values of f of a. Are you with me? Okay, once more, if we talk to this guy and we want to have a global one, this is the lowest thing in this area. So it is globally minimizing the point. Also for maximizing, for this guy, this is a global minimizer. The first one is a strict global minimizer. Okay, because it doesn't have equal points. For strict global maximizer, this is going to be the shape, it is the highest between them, and for the global maximizer, this is the peak, but it has equal points from both sides. Okay, this graph or this slide summarizes the various cases, and it's like a benchmark for you to summarize everything, but it has just only one of the signs is not, the inequality signs is not okay, it's not right, which is, just a second, if we are talking, this guy, the problem is here. This is f of x less than f of a, okay? I was trying to remember which one of them is not correct, and this is the not correct one. So f of x is less than f of a to have a maximizer. Do you read me? And if you have to have strictly maximizer, if it's just globally maximizer, it's going to have the equal sign. So just take care from this side, it should be the inverse. This is why in the coming slide it is correct. Everything is correct. And you have shape. to help you out in the slides, as I told you, if we are suffering that this slide is not clear enough for you, I've already sent you the slides to look at it, okay? Let's talk to this example. This example is very good by the idea. That's a curve, as you can see, which contains plenty of points. Some of them are minimizers or strictly minimizers, maximizers, and so on. So if I want to make the classification, we make the following table. I will classify based on a local for this part and the global for the down part. For the global upside, for the global part. If we are talking about a minimum, so we are in between two things. Either strict minimum or non-strict minimum. It's a minimum, but it's not a strict. But for the upper guy, it's just only the strict guys. For the maximization, we have also strict and non-strict. And same goes classification what goes for the global issue. So if we talk about in specific the points at -7 and at -2. Look at -7 and at -2. These two guys are local, minimum, and they are strict. Because you don't have points equal to each other at these two guys, in the neighborhood of these two guys. So that's the lowest within the neighborhood of its points, or of its neighborhood. Exactly the same like this point. It is the lowest extremum point at -7 with respect to the neighborhood. So this is, as you can see, it's a strict at -7 and -2. This is for extremum points, and the value of the function corresponding to them is 0 and the mean and the 4. Similar manner will go for this part, which is a minimizer. But this part is just only a minimizer, not strictly minimizing, because it has equal points without this interval. So this interval between 4 and 6, you will have a non-minimizer, and the value, these are the extremum points, and the extremum at this, or the extremum at 4 and 6 is the value of -3. In a similar manner, if you look to the maximizing for the strict, it will happen at 0, which will give you 3, which is the peak in the neighborhood of its neighborhood, and then at -5, which is also the extreme regarding the -5. So I have two strict extremum points, I'm sorry, -5 and 0. And the extremum values, the images relative to them, which are simply at 0, 3, or at -5, it's gonna equal 2 and 8, as you can see. Okay, let's go globally. The lowest point. Okay, let's see the lowest point on the whole graph. The lowest point on the whole graph, it's already here. I don't have a strict minimizers, but I have, okay, minimizers, but I don't have strict minimizers. Are you with me? Strict minimizer, once more, is once you have a point, you don't have equal points to this point. But for this case, this is the case where you have equal points. So if I want to complete the table for the maximization, for the minimization here, I'm sorry. So in the case of minimizing, for strict minimization, globally, there is nothing. There is no point, a specific point. But for the non-strict case, it's going to be between 4 and 6, and the image is negative. Going for maximizing, what is the maximum? I'm talking globally. What's the maximum point globally? Huh? Can you see a point which is the highest?
E.
For F.
F.
هنا مثلا؟
بس في أكتر بقى.
فين أكتر؟
هنا.
بس ده ما يروح.
Doesn't.
يبقى مفيش متصل او going up to infinity. لذلك لما اجي اتكلم على الستريكت, none of them exist. لا strict ولا non strict. Okay. Once more, life is all about optimization, as you can see. The elements, I will speak now about the elements of the optimization problem. any optimization problem in general will be formulated from two things. The objective function, and maybe you will have constraints or you don't have constraints, okay? So the first case, and it's going to be the topic of our next lecture, okay? Which is an optimization problem is defined by the objective function, minimizing, maximizing, and these are the main decision variables that's involving this function, okay? So optimization type. Objective function of the problem, find polyextremum and extremums, minimizes, and so on. Okay, that's the optimization. Decision variables, which are x1, x2, up to xn. These are the parts. The objective function f, optimize, minimize, or maximize. Constraints, which are conditions that they are like the boundaries of your choice. Sometimes we are dealing with functions or making an optimization with no constraints, okay? That's the case that we are going to talk about next time. Choice set of points in domain of which satisfy the constraints of the problem and getting the objective of this problem. Mainly, any optimization problem, it will form from two parts. Mainly, the objective function, which contains the decision variables, x1, x2, x3, or xy, or xy and z, whatever. These are the variables that you will have to identify their values. These are the extremum points. You will have to know the extremum points, which values from around these guys. And you will have the extremum, which is going to be the optimized case of this function. This is about the objective function. Also, you will have constraints, which are the boundaries of your choices. In order to have a feasible solution, you will have to get your solution which satisfies the objective function, but also doesn't make any of these constraints fail, okay? Or obey all the constraints that exist in this problem. Okay, classification of this problem. The unconstrained optimization, we will talk about it next lecture, inshallah. And it's just about a function, the objective function is given with no constraints. And that's the first case, like this guy, for example, which states that I have a convex and I'm looking for the least point to eliminate. Optimization with equal constraints. So I will give you the objective function, and then I will give you a set of equal equations. You will have to find, satisfy the maximum or minimum case of objective function, but obeying these equations. The last one, okay, so here is, for example, I will need to solve this guy, but with respect to one of the constraints, which is an equality. So I need to find the minimum point, but it should be within this constraint, okay, or within a point from these points. The most general cases, or the case, is to maximize an objective function subject to a bunch of less than or equal or greater than or equal constraints. In this case, we are talking about the case of inequality constraints. For example, x squared plus y squared, and we have x is greater than or equal to 0, y is greater than or equal to 0, xy should equal plus y less than or equal to 2, and we have a lot of techniques to deal with. We will see them. Okay, these are the shapes, these are the distribution or identifying your problem, because the first step into any solution is to identify your problem. So this is video. Any questions? Okay, I will continue tomorrow, inshallah, with the rest of this chapter in the case of unconstrained objective functions. Thank you very much. I'm really very happy to see you, and that I had the opportunity to see you today. Thank you.